I, Professor Neha Dikshit, going to explain you today one-dimensional element. This is the part in second unit from the finite element analysis. First of all, we will see when to use 1D elements. One of the dimension is very large in comparison to the rest of the two. Then that 1D element is used. As shown in figure, the length of that element as compared to the width and breadth is greater, so it is the 1D element. Element shape of one-dimensional elements is line. Additional data from user require remaining two dimension, that is the area of cross section. Element type in finite element analysis for the one-dimensional element is rod, or also known as bar, beam, pipe, asymmetric shell, etc. Practical applications for the 1D element in finite element analysis. We can use 1D elements in finite element analysis of long shafts, beam, in joints, connection, elements, etc. First of all, we will see rod or bar element. Rod or bar element is as shown in a figure. Number of nodes or rod or bar element is 2. Degree of freedom at each node is 1. So in this diagram, this is the first node and this is the second node. Okay, and degree of freedom at each node is only 1. Next is the beam element. Beam element as shown in figure, but the difference between the beam element and bar element is number of nodes of this beam element is 2. This is the first node and this is the second node. Okay, but the degree of freedom per node is 6, 3 in translations and 3 rotational. Next concept is discretization. We already see the definition of discretization in unit 1, but we will see in detail in this unit. Discretization. To make numerical method practical, number of degrees of freedom of physical system is reduced to the finite number. So we have to reduce the number of degree of freedom into the finite number of degree of freedom. The process of reducing degree of freedom to finite number involves dividing a continuous body into small finite element where two or more elements share a common node and or boundary line and or surface, which is known as the discretization process. Finite number of a smaller units is also known as the elements. Let's consider this figure. The body is divided into the 4 regions. The average cross-sectional area within each region is evaluated and is used to define an element with uniform cross-section. So this is the tapered bar, and we are going to divide this bar into the 4 sections. Body force and surface traction should be constant within each element. While dividing body, it is necessary to define a node at each location where a point load is applied. Accuracy of approximation can be improved by increasing the number of elements. So when the joining of element is there, then node is generated. This is the first node, second node, third node, fourth node and fifth node, while element is denoted number in a circle. This is the first element, second element, third element and fourth element. However, with increase in the number of elements, the amount of computation will also. This example clearly. This total element is divided into the 4 number of elements. So element 1 is having local node 1 and 2. See, this is element 1 and this element is having local node 1 and local node number 2. While the element second, the node 1 of element second is 2 and node 2 of element second is node 3. So node number 2 and 3 are the local nodes for the second element, while node number 3 and 4 are the local nodes for the third element, and node number 4 and 5 is the local node of the element 4. This is known as the discretization step. Next concept is internal and external node. Nodes are the point at which basic displacement are determined in finite element method. External node which occur on edges or surface of elements. This node is known as the external nodes. These nodes are common to one or two elements, and in this figure node number 1 and 2 is known as the external node. Now, one concept is there, that is the shape function. This concept is important for the further derivation. Let's see the one bar element and node 1 and 2 is there, and these are the natural coordinates. Zeta is equal to -1, zeta is equal to +1 for the second node, and zeta is equal to 0 for the 0 node. See, zeta is the natural coordinates, as global coordinate is denoted by the capital X, capital Y and capital Z, while local coordinates is denoted by the small x, small y and small z, and natural coordinates are denoted by the zeta, eta and psi. While the property of natural coordinates, it lies between the -1 to +1. So let's move towards the shape function. Variation of a different property such as a displacement, strain, temperature, etc. within the element may or may not be linear. In finite element analysis, these variations needs to be approximate within the element. In order to interpolate these properties within element, shape functions are used. In two-noded one-dimensional element, variation of displacement within the element is approximated to be linear. So this is the example of this figure, that is the explanation of this figure. That is the one-dimensional two-noded element is there, and variation of displacement, that is on first node u1 displacement is there, while on second node u2 displacement is there, and this is the variation. But if we need to find out the displacement at any point on this element, any point on this bar element, then we need interpolation function, and this interpolation function is known as shape function in finite element analysis. Two linear shape functions, that is the n1 and n2, are used to linear interpolation of displacement within the element. So below figure shows variation of a linear shape function, that is the n1 and n2 along the element. So at node 1, see this figure, at node 1 value of first shape function is 1, consider 1, and n2 is equal to 0, while in this figure at node 2 value of n1 is equal to 0 and value of n2 is equal to 1. So from figure A and B, first let's see the figure A. In this figure, this PD upon AC is equal to PB upon AB, and PD, what is the value of PD? Value of PD is n1. We need to find the interpolation function. So n1, and what is the value of AC is 1 unit, is equal to, what is the distance of PB? PB is, this total distance is 1, and zeta, 1 minus zeta is PB, while AB is total 1 plus 1 is equal to 2. So you will get n1 is equal to 1 minus zeta upon 2. Same here in figure B, pH upon Fg is equal to Pe upon Fe. So what is the value of pH? Value of pH is N2, Fg is unit 1, is equal to distance of P, it is the 1 plus zeta, and Fe is equal to 2. So N2 is equal to 1 plus zeta upon 2. So you need two shape function for the two noded 1D element, that is the n1 and n2, and value of n1 and n2 is 1 minus zeta upon 2 and n2 is 1 plus zeta upon 2, while zeta is the natural coordinates. Hence, using shape functions, displacement of any point P within element can be written in terms of a geometrical nodal displacement, that is the u1 and u2. How? Total displacement at point P is equal to n1 into u1 plus n2 into u2, while u1 and u2 are the displacement of node 1 and 2 respectively. So in matrix form, we can write as a u is equal to matrix n1 and n2 multiplied by matrix u1 and u2. Here un matrix is the elemental nodal displacement vector and capital N is the element shape vector. Similarly, local coordinate of any point P within element can be written as in terms of the n1 and n2, because n1 and n2 is the shape function, it is the interpolation function. So coordinate at any point P is equal to n1 into x1 plus n2 into x2, while n1 and n2 is the shape function and x1 and x2 are the coordinates of node 1 and coordinates of node 2 respectively. In general property PR, if you want to find out the property at any point P within the element and two another properties are known and shape functions are known, then property at any point P is equal to N1 into PR1 plus N2 into PR2, and this relation or this representation is also known as the isoparametric representation. We will see in a fourth unit what is the in detail what is the isometric representation. Next important topic is the stiffness matrix derivation. Now, what is stiffness and why do we need in finite element analysis? Stiffness K is defined as a force per length and unit of this stiffness is Newton per mm. Physical interpretation of the stiffness. Stiffness is equal to force required to produce unit displacement, and stiffness depends upon geometry as well as the material property. And in finite element analysis, displacement is equal to stiffness into the force. So what will happen here? Force generally you know, and stiffness is the property of the material and geometry. So you can easily calculate the stiffness. So displacement value you can derive from the equation, that is the displacement into K into F, because two properties are known, stiffness and force, and one property you want to derive. So displacement is the primary derived variable, while stresses and strain is calculated after the displacement is known as the secondary variables. So stiffness matrix for bar using direct approach we will see for the bar element. So stiffness matrix displacement equation for the bar element is K into X is equal to F. Suppose bar is subjected to the axial load, that is the P2, P1 and P3. So consider one element and having node 1 and 2 and load P is acting axially. So elongation is equal to X is equal to PL upon AE. So P is equal to AE upon L into X. So consider the unit displacement in direction 1. So force developed is equal to displacement is 1. So force developed is equal to P is equal to A into E upon L. So by definition of stiffness, stiffness at node 1 with respect to 1, it is AE upon L, while stiffness at node 2 with respect to 1, in node 2 axially but opposite direction load is acting, so it is minus AE upon L. Similarly, stiffness at node 1 with respect to 2, it is minus AE upon L, and stiffness at node 2 with respect to 2, it is AE upon L. So stiffness matrix K is equal to K11, that is the stiffness at node 1 with respect to 1 itself, K12 stiffness at node 1 with respect to 2, K21 stiffness at node 2 with respect to 1, and K22 stiffness at node 2 with respect to 2 node itself is equal to AE upon L common and 1 minus 1 minus 1 1. This is the stiffness matrix derivation for the bar element using direct approach. Now formulation of elemental stiffness matrix and load vector for a bar using shape function. So using shape function, strain is equal to, first of all, strain is equal to change in displacement. So del u by del x I can write, and del u by del x is equal to del u by del zeta into del zeta by del x. So we know that zeta is equal to 2 into x minus x1 and x2 minus x1 minus 1. So partial derivative of this natural coordinate zeta, del zeta with respect to x is equal to 2 upon x2 minus x1. So value of this variable del zeta by del x is equal to 2 into x2 2 divided by x minus x1. Again, displacement I can write in the form of the matrix and shape function n1 n2 into u1 u2. So partial derivative of this displacement equation with respect to zeta is equal to del n1 by del zeta and del n2 by del zeta, and another matrix is u1 and u2, and n1 is equal to 1 minus zeta upon 2, also n2 is equal to 1 plus zeta upon 2. Put the value of n1 and n2 and derivate this equation partially with respect to zeta. So you will get minus 1 upon 2 and 1 upon 2 u1 and u2. So del U by del zeta is equal to 1/2 minus 1 1 and U1 U2 in a matrix form. So previously we already seen that as the strain is equal to del U by del zeta and del zeta by del x, and put the value of both variables and you will get epsilon strain is equal to 1 upon x2 minus x1 in first matrix minus 1 1 and in second matrix u1 and u2. So epsilon is equal to b into un, while epsilon is equal to elemental strain. B is also known as elemental strain nodal displacement matrix. It is 1 upon x2 minus x1 into in matrix minus 1 1. So in short, x2 minus x1 is the length of the element, so 1 upon L into in matrix minus 1 1. Also sigma, that is the stress is equal to modulus of elasticity into strain, and value of strain is equal to, that is epsilon is equal to b into un. So sigma is equal to stress is equal to E into b into un. Let's see the one example on a step bar. Using direct stiffness method, determine the nodal displacement of a step bar as shown in figure, while material properties, that is the modulus of elasticity, is given for the both element. Forces are given. First force is 10 kN, second force is 5 kN, and cross sectional area of both elements are given. So first of all, first is to solve this numerical using the finite element analysis. It is the discretization. So we already discretized this element in element number 1 and element number 2. While this element number 1 is having the local node 1 and 2. Okay. And for the second element, which are the nodes 2 and 3. Okay. So now the diagram says that at node number 2, one force is there, remember, and at node number 3, another force is there. At node number 1, 10 kilonewton force is there, and at node number 2, 5 kilonewton force is there. So first of all, we will see what is the dimension of stiffness matrix and force matrix. So total degree of assembly n is equal to degree of freedom per node. Bar element is there and degree of freedom per node is 1, also into number of nodes in assembly. Total number of nodes 1, 2 and 3. So 1 into 3. According to that, dimension of a global stiffness matrix is 3 by 3. Global load vector is 3 by 1 and dimension of global nodal displacement vector is 3 by 1. So first of all, we will calculate elemental stiffness matrix. How many elements? 2 elements. So K1 is equal to A1 into E upon L1 into 1 minus 1 minus 1 1. In this figure, cross sectional area is different and length is different. So denote that cross sectional area and L with suffix of element number. So put the value of area, E and length, and in matrix form it is 10 raised to 5 into 6 minus 6 minus 6 6. While element number 2 stiffness matrix is A2 into E upon L2 1 minus 1 minus 1 1. In this, K2 is 10 raised to 5 into in matrix 1.4 minus 1.4 minus 1.4 and 1.4. So global stiffness matrix, we already seen that the dimension of a global stiffness matrix is 3 by 3. So let's see, K is equal to K1 and K2. So what is happening? We need to add, while K1 placed on the diagram, on the total stiffness matrix on position 1 and 2, because local nodes for the first element are 1 and 2, while local nodes for the second elements are 2 and 3. So according to that, in 3 by 3 matrix, place each element in that position and you will get K is equal to 10 raised to 5 and multiply by 3 by 3 matrix, and these are 1, 2, 3 are the total element degree of freedom, that is a global degree of freedom. Next equation, global stiffness nodal displacement load relationship, K into UN is equal to F. Okay, so 10 raised to 5 into stiffness matrix into displacement is equal to, now at first node fixed support is there, so we will get reaction force there, and at second node F2 force is there, and at third node F3 force is there. So applying the boundary condition, as first node is fixed, so displacement at that node is equal to 0. So we easily get U1 is equal to 0. Put the value of F2 is equal to, it is in negative x direction, so minus 10 into 10 raised to 3 in Newton, and F3 is equal to 5 into 10 raised to 3 in Newton. Put the all values. So as U1 is equal to 0, using elimination approach, first row and first column will get deleted because U1 is equal to 0. So remaining matrix is 10 raised to 5 in matrix form. First row is 7.4 minus 1.4, second row is minus 1.4 and 1.4. U2 into U3 is equal to minus 10 into 10 raised to 3, 5 into 10 raised to 3. So all variables are known, and you can easily convert this matrix in simultaneous equation, and solving that equations you will get U2 is equal to minus 0.1583 mm and U3 is equal to minus 0.1226 mm. Remember to give units. It is so in this video we seen what is the 1D element and when it is used, what is the stiffness, what is the importance of stiffness, derivation of a stiffness for one-dimensional bar element, and numerical on that bar element. So thank you for the listening.